Welcome back, everybody. I'm happy that you found your way back after the coffee break, and I hope that the caffeine is kicking in now. I know how difficult it can be for everyone, especially with a jet lag, so we have compiled interesting topics, and I hope we can keep your attention throughout the next couple of hours. So my name is Anne Tipka. I am a software engineer in the software application section at the CTBTO. I am very happy, and I have the pleasure to introduce the next panel to you, which is designed to broaden our understanding of what a changing environment means to the CTBTO, especially in the operations and how environment conditions affect our local and especially our global monitoring. And just this morning, maybe you remember our Executive Secretary, Dr. Robert Floyd, said that our international monitoring system is 90% ready, and that we have, over the years, 10,000 times more throughput in data. So you can imagine how important it is to keep our resilience and maintenance up for the coming decade. And the ever-changing and ever-evolving environment is important. Think about extremes like flooding, sea level rise, or even about the earthquakes that we heard yesterday in the keynote talks. These are all challenging, and we need to make sure that our international system that we rely on for verification and security is up and running. We want the session to spark forward-looking discussions, not only how we adapt our own systems, but also how we can use our data for expertise and our expertise for the future to the general community. So what I want to do now is to introduce first our keynote speaker, Dr. Lawrence Ruhl, who gives us a very interesting insight of what the European European Center, I'm sorry, that was my, the European Center for Medium Range Weather Forecast, also short for ECMWF, maybe you heard this before. She is the director of the Copernicus Atmosphere Monitoring Service at the ECMWF, and she will give us a topic about recent highlights of numerical weather prediction and atmospheric composition forecast at the ECMWF, especially with a focus on the role of observations, which is a perfect match since we have the huge IMS system that we need to maintain. That's the perfect entry point, and the long experience they have at the ECMWF with the amazing number of in situ and Earth observation data sets is just a good entry to the panel discussion we have afterwards. And the ECMWF holds one of the largest meteorological data archive nowadays, which is also something we can learn of. So please join me with a warm welcome for Dr. Lawrence Ruhl.
Thank you very much, Anne, and good afternoon, everyone. Many thanks for this invitation. This is a pleasure to be with you and to have the opportunity to talk about some developments that we carry out at ECMWF, so the European Center for Medium Range Weather Forecasts. So first, 2 slides maybe about who we are. So ECMWF is an intergovernmental organization that has been created by a group of nations, of countries, who had the vision of a collective endeavor to improve weather forecasting. And at that time, it was in 1975, weather was predicted 1-2 days ahead. And everyone was aware of the fact that to predict for longer ranges, a common significant effort was necessary. And this is a target that has been given to ECMWF when it has been created on the 1st November of 1975. So this is an organization which is the headquarters of the organization is located in the UK, in Reading. We are about 500 people, a bit more maybe. We have 23 member states and 12 cooperating states. And in 1921, we have become a multi-site organization with a part of our activity, especially the one dedicated to the implementation of the Copernicus services we are responsible for, and EU research projects. So the EU-oriented activity is based in Bonn, and we have a high-performance computing center located in Bologna. The collaboration, ECMWF grew with an active collaboration with its member states, with its cooperative states, of course, but with also other organizations, WMO, the World Meteorological Organization, but also space agency like ESA, the European Space Agency, or EUMETSAT, and as I just said before, with EU bodies for the implementation of the Copernicus services, the ones dedicated to atmospheric composition and the one dedicated to climate change. And also for the implementation of Destination Earth, which is a digital twin of the Earth, and various research projects. And with CBTBO, we have started a good collaboration since 2003 as well. ECMWF, the main responsibility of ECMWF is to provide good medium-range forecast. And to provide such forecast, we run and develop numerical weather prediction systems. And here, this is just a picture to show you the evolution of the performances of our system. In fact, if we look backward, so almost 50 years ago, when we have been created, we can say that we have more or less earned 1 day of forecast every decade. This is what is shown on this scheme. What you see is what we call the anomaly correlation coefficient, which is a measurement of the performance, the quality of our forecast. This is for the two-dimensional geopotential field at 500 hectopascal, something like mid-troposphere, and the correlation is between the forecast and the analysis. The analysis is for us a reference because it assimilates all the observations that we have. And you can see the evolution of this correlation. Of course, when you reach 100%, this is perfect. Looking at the lead time of the forecast on the northern and the southern hemisphere. So, for instance, in blue, this is the easiest part of our work. This is a short-term forecast, 3 days ahead. And in yellow, this is the most challenging one with 10 days ahead. And what you can see, comparing the red one and the green one, which relates to 7-day forecast and 5-day forecast, is that finally we have achieved now, in 20 years, the same kind of performance for the longer range. So this is just to illustrate how it works. And you can imagine that there are several parameters that allow us to reach such a performance, and observations play a key role. In fact, what we can say is that our performances, the reliability of our forecast depends on the capacity of our numerical model to simulate the full Earth system. So not only, of course, the atmosphere, but also the interactions with land, ocean, sea ice, atmospheric composition, and also the interaction between each of those parameters. So developing global systems that could integrate those interactions, this is one thing. The other thing is our capacity to assimilate in those global systems numerous observations that can define the initial conditions that will initiate the forecast. And here I would like to highlight, talking at the global scale, the essential role played by Earth observation, actually. They Earth observation are systems that provide an overview of the situation at the global scale, initial state of the atmosphere at the global scale. So this is one point. The other point is that when you talk about Earth observation, you talk about systems that are good resilience regarding their sustainability, and certainly they are less sensitive than in situ networks that are also assimilated in the system to extreme events. So this is for us extremely important to elaborate on Earth observations. And And just a slide to show you the evolution of the number of observations that we assimilate in our systems. So this is for the integrated forecasting system. So we have at ECMWF IFS, which is our global forecasting system. And today we assimilate every day 60 million of quality control observations. And amongst those 60 million, 40 million come from Earth observation, from satellite observation. And you can see here, this is year by year, the evolution of the number of observations, that satellite observations that we assimilate now every day. We have talked about the observation, about the physics-based model, but nowadays we also have to talk about, of course, artificial intelligence and machine learning, because this is a future. And I have to say that we have started to work hard on the implementation of AI version of our forecasting systems. And now the system that we have, I have to say, outperform physics-based system, particularly for forecasting synoptic situations. And thanks to AI ML, we have earned one additional half day in our forecasting lead time. Of course, so what you see here is the same parameters, so the anomaly correlation coefficient, that when it reaches 85%, which is a good performance, and you see the evolution of this target when this target is reached for various systems, various numerical weather prediction system. So on the top, on red, you see the IFS performances, and the small parts, the short curves relate to AIFS and other artificial intelligence-based system. And you see that it outperforms quite significantly the physics-based model. However, there are some caveats. Not all variables are available, are covered by the AI system. And generally, I've said that they perform very well for large-scale pattern, but for small-scale pattern, this is not really the case. And of course, you need to train the system with good data, with good reanalysis, and this means that this is a combination of physics-based approach and AI that will support development of reliable systems. To do what? To predict weather forecasts. And as I said at the beginning, I've talked about the importance to have a global overview of the Earth system. So it means that we are also able to provide some useful insights to deal with other issues like floods, wildfires, climate change, or atmospheric composition, CO2 emissions, and this is exactly what is now done at ECMWF. So we provide numerical weather prediction for the next 2 weeks, seasonal, subseasonal prediction, but we also provide information about climate variables, about air quality at the global scale, greenhouse gases forecast at the global scale, but also information about hydrological forecast and wildfires. We have developed this part of our activity thanks also to the programs that we that the European Commission asked us to develop and to implement. So I would like to talk briefly about the Copernicus program. So this is a program developed under the space program, and this is the Eye on Earth program of the European Union. In 2014, ECMWF has been nominated as an interested entity by the European Commission to implement the Copernicus Atmosphere Monitoring Service and the Climate Change Service. And since 2021, we are also in charge of the implementation of the Destination Earth digital twin of Earth system. We don't work alone. Of course, we work with many partners. This is an actual community. Here, this is just to give you an overview of the situation for the program I know the best, the Copernicus Atmosphere Monitoring System. We have celebrated the 10 years of camps and C3S at ECMWF last year. And last week, we had the General Assembly with more than 400 people, and among those 400 people, there were representatives from the 200 contractors, partners who work with and for us, for the implementation of those services. So this is an actual European effort to implement operational system based on cutting-edge science to monitor in the best way atmospheric composition. And of course, talking about atmospheric composition, we rely on what we develop at ECMWF for numerical weather prediction. So we have developed the IFS Compo version. IFS Compo means IFS atmospheric composition. And also, for this activity, we use, I don't know if if it will work, but just to tell you, it should be an animation, but we assimilate information from Earth observation, from satellite, to initialize with analysis, with relevant analysis, our atmospheric composition forecast and our air quality forecast at the global scale. And this is something running in a full operational way, like numerical weather prediction, and forecasts are available twice a day of atmospheric composition. Exactly like for what we do for numerical weather prediction, we assimilate in situ observation data, of course, but also many Earth observation data sets coming from various missions. And here you can have an overview of the missions that are used to run the atmospheric composition part of the system. We are very happy because this year is a nice year. Several missions have been launched. Copernicus missions have been launched. One in July, the last this year, two months ago. This is a mission MTG-S1 with the satellite, the instrument Sentinel-4 embedded on. Sentinel-4 will be embedded on the geostationary platform, which is focused really on atmospheric pollutants, which means that we will have, when the instrument is operational, we will have, with a high frequency information about atmospheric pollutant columns, concentration columns, over the whole of Europe and the north of Africa. This is the first time that we will have such information. And last month, at the beginning of August, Sentinel-5 was launched, focused on both air pollutant and methane, but this is not a geostationary platform, but this is a lower orbit platform, but a lot is expected because the instrument will provide very high resolution information. And with that, we can visualize, monitor a number of events related to atmospheric composition that impact the atmospheric composition and that impact also our lives. Like this is, I will give you example, wildfire monitoring, for instance, and their impact on emissions and air pollution. So here you just have an example of the various systems that monitor wildfires. This is based on Earth observation, on satellite observation. We have an aerosol alert system, which allows us to monitor where there are unexpected high level of PM of aerosol everywhere in the world. It can be wildfire, but it can be something else, like dust or like anthropogenic pollution. And you can imagine, so here this is just a retrospective movie of what happened in 2024. So all the wildfires that we have monitored last year. And of course, this year, sadly speaking, we have monitored the terrible fires that happened not only in North America, but also in Europe this summer, with an amazing amount of air pollutants emitted by such wildfire, and a record regarding carbon emission already broken by Spain. And here, this is just, so we monitor this since 2003, and this is just to show you the annual wildfire carbon emission for Europe that have been recorded by the CAMS systems. I've talked about the geostationary satellite that will provide us some information over Europe, but we already work with geostationary information from satellites focused on Asia and North America. So this is just an example of the retrievals that we assimilate in our system at a global scale today, to improve quite significantly the quality of the forecast, of the air pollution forecast that we provide every day. And usually we assimilate Earth information, satellite information, and in situ observations are used to evaluate, assess the quality of our forecast. And here, this is just an example for nitrogen dioxide and ozone, with a quite significant good improvement of the performance of the forecasting system when Earth observations are assimilated. And with that, we are able to provide, I hope, useful information about air pollution events, so what relates, of course, to health impacts. So just here an example of Saharan dust intrusion that crossed the Atlantic. It was this year, once again, during this summer. So coming from the Sahara, this is the plume in blue, and impacting on the other side of the ocean, Atlantic Ocean, the Caribbean. And we also have monitored very impressive air pollution episodes due to anthropogenic emissions. I mean traffic, residential heating, industry in Asia and in other parts of the world. This is just an example here that I present. Once again, we always compare the forecast with the observations, in situ observations that we have, to be sure that the information that we provide is improved time after time and is reliable, so that people could be informed and decision makers could take the appropriate decisions. I wanted to show another example of how we use Earth observation in our system. This is a bit different. In fact, this is to detect some exceptional sources. And we have launched at the beginning of this year, it was in February, this new application on our website, which is the CAMS Methane Emissions Hotspot Explorer. It's based on Earth observation from an instrument which is called Tropomi on a Sentinel-5P satellite, and it measures methane columns, and thanks to artificial intelligence, machine learning system, and also knowledge of what we could expect regarding emission, we detect hotspot, unexpected hotspot, and we allocate those emissions to various sources, like oil and gas industry, coal mine, or landfills, should be large point sources. And just to an example, very interesting example, we have detected, it was at the beginning of this year in January, an amazing amount of methane emissions in Africa that was not expected at all, not in the emission inventories that are used. And looking more deeper into this, we have understood that it was located at the Mont Fontaine, which is a volcano, and the emissions were due to the activity of this volcano, and it was completely unexpected. So this is a kind of thing that we do using artificial intelligence, but also inverse modeling to evaluate from what we observe, from what we expect with our model, looking at the difference to evaluate unexpected emissions. And I think that this is also where there are some linkages with what is done at CBTBO. And we do that also for CO2. This is one of the main topics that we have to deal with. We have been required to deal with by the European Commission, developing what we call the CO2 MVS system, MVS for monitoring, verification, support capacity. So this is a capacity that the European Union would like to implement to assess how international agreements, like the Paris Agreement regarding CO2 emissions, are reached or met. And this is more or less the same kind of thing. We use Earth observation, in situ observation. We use inverse modeling to assess the emissions, to evaluate the emissions thanks to observations, comparing what is reported in the emission inventories, what is reported in policy framework to what is observed. So this is just an example of what we have already done. This is a prototype, in fact, with a comparison also of our inverse modeling analysis to emission inventories, current emission inventories, but also other systems. So what we do is in yellow, with a priori estimate in yellow and a posteriori estimate assimilating observation in orange. And you see that it's quite consistent with what is carried out in other frameworks. So I think that I will stop here, just to say before that we have an open data policy that is now very active since 2020. ECMWF will open its near real-time data in 2025, so this year on the 1st of October, so certainly stay tuned, but you will be informed about that. And just a few takeaway messages. Space-based observation are really critical to allow accurate forecast and to provide advanced weather, air pollution, extreme event warning system at the global scale. This gives a global overview, and this is certainly less exposed to extreme conditions and in situ networks. So this complementarity is absolutely critical. European satellite constellation are unparalleled. That's great, what is achieved today by the European Union, providing wealth of observation based on various sensors. And investment in observing system and in AI, of course, is also absolutely critical. This is obvious, but certainly the observation-based prediction system will improve and expand further in the future, and it will give more, I would say, useful insight for our life, and just to raise that this is absolutely critical to develop a resilient framework to have them performing in the best way. So many thanks for your attention.
Thank you very much. thank you very much for your very interesting topic. And I think it gives us some good ideas, and it was a comprehensive overview. So, according to the time, we need to move forward, but I would like to have at least one question. So I have two, okay, very short ones, okay? Yeah, please use the microphone. Thank you.
Thank you very much. Nice, very nice presentation and amazing work. I actually have two short questions. The first one, which weather application do you have on your cell phone? And the second one, do you have any plans to incorporate probabilistic events like volcano, something like volcano and earthquakes in your future work?
Yeah. So on my application, on my cell phone, I have windy application because it uses ECMWF data for weather forecast, but also for air pollution. And yes, I didn't talk about such applications like volcano, but obviously we can detect a lot, also thanks to Earth observation, and we have some application regarding. So what we do with volcano within camps is the monitoring emission of SO2 typically, and SO2 is very well monitored from space and from in situ network, and we have developed a specific work to assimilate SO2 observation and to assess, yes, the strength of the volcano regarding the impact on SO2. This is what we do. Yeah, yes, absolutely.
Can I ask you to do this in person with Dr. Ruhl? Because we need to move on. Thank you. So, thank you very much once again. Huge applause for Dr. Ruhl.